everything that we've looked at with motion so far, all of our formulae have been in terms of time. Okay? In extension, and extension 2 for that matter, we don't limit ourselves to that. We also look at it in terms of the displacement. So velocity be some function of x. Now, if that's true, the relationship we have is that the acceleration is the derivative of half velocity squared with respect to x. Okay? So when we're dealing with time, we can just differentiate with respect to time, that's fine. But if it's with respect to displacement, we can't just differentiate it with respect to x. We have to differentiate a half v squared with respect to x. Here's a quick little proof why. Well, we know the acceleration with respect to time is equal to dv to t. Okay? So as I say, you can differentiate velocity with respect to time, we're fine. I could rewrite that as dv dx times dx to t. Now, dx to t is just velocity. So I now have dv dx times velocity. Another way of writing velocity, you could write it like this. d to v of a half v squared. Because if you differentiate a half v squared with respect to v, you'll get v. But now the dv's cancel, and you have your d dx of a half v squared. Yep.
Why can't you just stop at v to dx?
V to v dx is also a very handy way of using it in some questions. So a lot of times, yes, we will use v to v dx. Yep. Alright, so we've got a particle, straight line, accelerations in terms of displacement. We're going to find the formula for velocity in terms of displacement, and we've got some initial conditions there. So right, we know d dx of a half v squared is the acceleration. So a half v squared, 3x minus x squared, plus a constant. And subbing in. So it's the same sort of idea, but the difference being is we can't just integrate velocity or differentiate velocity. It's half v squared we're working with. And there's our equation, v squared. Well, it wants an expression for velocity, not velocity squared. Now, velocity is plus or minus. You think, well, hang on, how can something have both a positive and a negative velocity? Well, it can, because time is no longer involved. It's just at different times. We're saying at this position, at one time it'll have a positive velocity, but another time it might be coming back and will have a negative velocity. So it is possible to have both a positive and a negative velocity at a particular position. If I did it, and as you said, why wouldn't you just use v to v dx? Which personally I probably would. Because then I can use the idea of definite integrals. It makes life, I think, a little bit easier. So if I have v to v dx is 3 minus 2x, if I separate the variables, I can now write that as the integral of v to v is equal to the integral of 3 minus 2x dx. And again, we match up the limits. So down the bottom I've said, well, when x is 1, velocity is 2. I'm trying to find a formula that will link displacement and velocity. Now, you'll notice the first thing that will happen, when I integrate v with respect to v, I'll get half v squared. So it still appears. And that one we're going from v to 2. The other side we're going from x to 1. So subbing in, tidying up, and you can see, well, again, we get v squared is 6x minus 2x squared. Alright, some things to note. We know velocity squared is always going to be positive. Okay? So this allows us to find the path of the particle, because we can substitute in the 6x minus 2x squared and say, well, that's always going to be greater than or equal to 0. If I was to solve that inequality, eventually, I'll get that x is in between 0 and 3. And so that tells me how this particle is travelling. It's a very simple bit of motion. It's just going between 0 and 3, and that's it. It's never anywhere else. Alright, let's try another one. Acceleration 3x squared. Particle is 1 unit to the right. Velocity of root 2 in the negative direction. We're actually going to find x in terms of t. So we're going to go right back and find the displacement equation in terms of time. So d dx of a half v squared is 3x squared. So half v squared x cubed plus some constant. Eventually we get our constant being 0 for this one. V is plus or minus the square root of 2x cubed, which again is okay because you can have a plus or minus. Let's do it the other way. So with the v to v dx, then I would separate it. The link I've got here was when x equals 1, velocity is negative root 2. We're trying to find a link between displacement and velocity. So integrate, sub in, and again we come up with the same equation. Well, that's velocity squared in terms of x. We're trying to get x in terms of t. I could do that because velocity is of course dx to t, but you'll notice I've chosen minus the square root of 2x cubed. It's no longer plus or minus. I have to make a decision because our calculus deals with functions, and functions, for any x value you have a maximum of one y value. So I can't have plus or minus to do the calculus. So why do I choose the minus root 2? Well, I'm matching the initial conditions that I'm going to use to find the constants and the things like that. And so in this question, when I substitute in x equals, 1, I need to get an answer of v is negative root 2. So when I substitute in, I need the negative square root of 2x cubed. If I took the positive, I'd get a positive velocity. So that's why I'm using that one. Now it's dx to t. Oh, I'll tidy up the indices. I can keep going. Well, that's dx to t. Turn it upside down, make it the t dx, and we can integrate again. So we've got the t dx is minus a half root 2 x to the minus 3 on 2. So t equals, add 1 to the power over the power. Let's find the constants. We said initially it was at x equals 1. So subbing that in, I get a constant of minus root 2. And we get this lovely expression. T equals the square root of 2 on x minus root 2. Not quite good enough, because the question was find x in terms of t, not find t in terms of x. So now we have to make x a subject. Before I do, had I done it by definite integrals, then I would have separated the variables. The linkage was t equals 0, x equals 1. Well, this one here on the left, when I just have an integral to t from 0 to t, I don't bother writing out t. I'm going to substitute in 0 to t. It's just t. The right hand side, however, we do work that one out. Sub in x, sub in 1, and they are the same expression, although that one's factorised. Okay, so t plus the square root of 2 is root 2 on x. Square both sides. We're trying to make x the subject. So turn upside down, divide by 2. No, multiply by 2 once we've turned upside down, isn't it? And we get 2 on t plus root 2 all squared eventually. Interesting little path the particle travels on. Let's have a look at an HSC one. Okay, travelling along the x-axis as our little particles love to do. 2 metres to the right it's starting at, and just in case you weren't sure what that meant, that is x equals 2 and t equals 0. Initial velocity of 5, acceleration, show that the velocity is x squared plus 1. Okay, so I can say d dx of a half v squared, 2x cubed plus 2x, half v squared, integrate, sub in the conditions, 2 and 5, we get our constant is a half. So v squared is x to the power of 4 plus 2x squared plus 1. Or, it's a stretch. Had I done it as a definite integral, separate the variables, link the 2 and the 5, and eventually we get to the same stage. So there we are. That's what v squared is. Fortunately, look at it. It's a perfect square, which was nice. So v squared is x squared plus 1 squared. Now, the biggest mistake people made this particular year was to then go, well, therefore v is x squared plus 1, which is what they want. Not correct. At this stage, v is plus or minus x squared plus 1. You have to justify why it's the positive case, not the negative case. So, v is x squared plus 1? No. Where's my... need a justification. So the reason I chose 0 was, well, I simply said we need to satisfy the initial conditions. But you need to show that, hey, I did consider there was a negative case. This is why I discounted it. Something like that. Right. Hence, find the expression for x in terms of t. So now I'll write velocity as dx to t. I'll just go the way I prefer. So separate the variables. Anyway, we've got inverse tan. So t is inverse tan x minus inverse tan 2, but that's t in terms of x. We want x in terms of t, so inverse tan of x, and that's probably good enough for a final answer and for mere mortals, but tan plus tan on 1 minus tan tan. There you go, tan t plus 2 on 1 minus 2 tan t. Alrighty, let's add that question.